also in our midst. So I want to welcome Mr. Dr. Akini Idamilola. You're welcome. So I will be making this last section while I hand over the rest of the coordination to him. So we are moving on to the third section right now, which is about the material science. And so I'll hand over to Mr. Hiwe Idorenyi, who is going to coordinate this section. Thank you so much.
All right, thank you very much and welcome to the material science session. So in this session, we're going to have two presenters. Please, can you hear me, please? Can you hear me?
Yes, we can.
All right, so the first speaker is Dr. Olubade Timitope from the Department of Mechanical Engineering of the City University of Hong Kong. So he's an expert in surface engineering of mechanical systems, which is just to reduce corrosion. So today, he will be walking us through his latest method of corrosion control. So the second speaker here is going to be Ms. Onyanga Kindness. So she's also from the City University of Hong Kong, from the Energy Harvesting and Wearable Energy Technologies, from the School of Energy and Environment. So she's also an expert in the energy conversion technologies. And today she's going to tell us about her latest discovery, which is centered on the organic solar cell technology. And each of the speakers is going to have 7 minutes to present and 3 minutes for a Q&A, which is going to be solely directed by me to ensure orderliness. So I would like all the participants to fill out the assessment forms to give quality feedback to the presenters. At the end of these presentations, we will learn about the latest technology in corrosion control, which is something that we need so much in our oil and gas industry. And also the knowledge that we're going to have from the solar cell technology, I think is going to help us to advise our government if we have the opportunity. We're going to advise them on the need to diversify our power sector. So be attentive while we kick off this presentation. I would like to usher in Dr. Timitope to carry on with his presentation. Thank you very much.
Thank you, Mr. Moderator. Thank you very much. I'm going to share my screen so that I can start this presentation. Please, can you see my screen, please?
Yeah, go ahead, go on.
Okay, thank you again. Thank you for allowing me to speak my presentation. I'll be talking on the passivation behavior and corrosion properties of surface mechanically treated 17.4 pH stainless steel. Temitope Olubade, Mechanical Engineering Department, CTU. Quickly, I will report the material and method, the result and discussion about the surface treatment we apply on the material to actually create surface region on the material. Then I will conclude this presentation. A very quick background. Most material failures occur on the surface of the material, and this is actually leading to degradation of material from the surface to the core region of the material. And then because of this problem, there is a process on ground that has been developed. As you can see, we have 3 of them: the coating or deposition, the hybrid nano-crystallization. However, the major problem that is associated with this coating and the last method is that the chemical composition of the substrate and the material is somehow different, and this may actually lead to problem. Most importantly, there's a relatively poor bonding between the surface layer and the substrate, and this also leads to a very poor corrosion resistance. Hence, we come up with a method, as you can see with my cursor. This method creates a nano grain layers on the surface layer through plastic deformation. And the most important thing about this method is that it improves the mechanical properties of the material: hardness, yield strength, ductility, and tensile strength. Now, we have various forms of this surface treatment. But among this surface treatment, we have one particular one that is being developed in my group, which we call surface mechanical attrition treatment. This method involves the bombardment of the surface of the material with a very fast, high-moving balls. As you can see here, we have the resonant spherical balls. The ball moves at a very, very high speed, hits the surface of the sample, create a nanograin layer on the surface of the sample, then create a nucleation site, thereby enhancing the property of the material. And one good thing about this method is that it improves the properties of the material without changing the overall composition of the material. And the material has been applied to materials in our group, and some of them have been published already and made known to the public. And recently, we summarized the properties of the materials after we applied this method, and that has also been published in Nanomaterial Science. This shows that this unique SMART method has been widely recognized as a method that can be used to enhance the properties of a material in terms of mechanical and in corrosion properties. Now, that is mechanical properties. Let's come to corrosion property. The properties in terms of potential, current density, Nyquist plots, maximum phase angle, impedance, and Matuszewski analysis, and the stress corrosion cracking behavior. Also, methods can be applied in two forms. Now, we want to apply the SMART method to improve the mechanical properties and also to improve the corrosion properties. I hope you get the logic. Now, the major material we use here is the 17.4 pH stainless steel. This material is chosen because of its very good attributes, which include the high toughness, ease of fabrication, and high hardness for enhanced durability. And this material finds application in many automobile and aerospace and oil and gas, petroleum industry. In fact, in most manufacturing companies. But most especially, this material is peculiar to aerospace and automobile industry because they use this. So it's a very hot cake material for automobile and aerospace industry. However, there's a problem. The problem is that this material experiences failure under aggressive corrosive environments. And then when combined with some tensile strength and corrosive environment, this material also fails. And that is why we come up with this method to see if we can correct this problem, improve the properties of this material so that it can be fit for this company and reduce the level of corrosion to the minimum. And it can serve as supply to most companies that we have around. Now the TEM process says that there's a structural a longitudinal about 50 nanometer grain on the surface of the material, and we have some dislocation clusters on the surface of the material, and this actually contributes to the improved properties of this material. And in terms of corrosion properties, combining SMART and annealing treatment, you notice that our sample experienced a very low corrosion current density. And from literature says that the lower the current density, the better the corrosion properties. And this actually shows that we have an improved property. We went ahead to do the surface element analysis to see if we can actually characterize this material. And our method shows that all the elements that are in this sample, they contribute to the corrosion properties. Also, I can see here, the amount of chromium in a sample play an important role in corrosion properties. We notice that our sample that is treated with SMART annealing has the highest level of chromium, which shows that it has the most important corrosion properties. And also the ATM study shows that we have so many elements in the sample, which leads to uneven distribution of elements. But in particular, we have one element, which is very high density copper-rich precipitate in it, and this precipitate contribute to the improved properties of the sample in terms of and corrosion properties.
Please,
and
you
it's also the distribution of the.
You have more 30 seconds.
Yeah, sure, I know. Sure, I know. And this is a summary of the APT that's also talking about the improved properties of the material. And this is also part of it. And the corrosion reaction shows that we start from dissolution of ion to ion 2 ion and generation of hydroxide ion and formation of local alkaline elements, and all this contribute to the corrosion reaction. And in summary, this is the corrosion mechanism from passivation to transpassivation and passivation, and this actually prevents the pitting corrosion. And the major application is the fabrication of the turbine blades, In conclusion, this can be summarized in form. That is, number one, we have an ultrasonic Bohr bombardment on the surface of the sample. This creates a surface layer on the sample. And after this, it increases the free energy within the sample. Thereby, the plastic deformation activates its location. And with more plastic deformation, the dislocation accumulates and form some density. And from here, we have boundaries that are divided into several regions. And this opens a nucleation through which chromium can move from the bottom of the surface to the surface of the material, thereby creating a passive layer on the sample and preventing corrosion to the minimum. And this is the future work. You can extend this work to other parameters and other alloying ends. These are this project. Thank you for your time. God bless.
All right, thank you very much. You can give Dr. Temitope a virtual clap. Thank you for that. Please, to remind you, we have a link where you can send your assessment, where you can send your questions to Dr. Temitope. But in the meantime, we will take like 1 or 2 questions. Any question, please? Do we have any question, please?
Hello, may I ask a question?
Oh, yes, go ahead. Thank you.
Yeah, thank you very much.
Go ahead.
Well, as you know, I'm in the social sciences, so this is not
Sure.
actually my field. But I like to look at it from this angle. I want to thank Mr. Dr. Tokpe. I'm sorry, I forgot your surname, but he's my good friend. Now, I want to know, how can this be applied to Nigeria? What can we do to actually have this kind of research, the outputs in Nigeria? Thank you.
Yeah, thank you very much, Robert Midile. Actually, the focus of this research is centered on the oil and gas and the automobile industry in Nigeria. This is the focus of the research, and we notice that we have a very high rate of corrosion in most manufacturing industry in Nigeria. So I come up with the idea that this method exists here. We can actually adopt this method to upgrade our materials in Nigeria, prevent the corrosion to the minimum, and also improve their properties so that by the time we are using them in oil and gas, especially in downstream sector, we have some pipelines in water for a very long time. We can actually use this method to create a nanograin layer on the surface of this pipeline inside the water. And this nanograin layer will generate a structural layer on the material, thereby preventing the corrosion, at least prevent them for a very long time. And this can actually reduce the cost of production and fabrication in the industry. So the idea actually started from applying it to solve the problem in Nigeria. So we have the method here. So we use the method to solve the problem in Nigeria. And I'm very sure by the time we return to Nigeria, God's grace, I'm going to apply the same method to actually see if we can solve those problems in Nigeria and provide solution to them. And this will help their long-time problem they have been facing in terms of corrosion. So thank you very much.
Okay, all right, thank you very much. Thank you very much. I think we're gonna take this back home. And if you know anybody in government, if you know anybody in the oil and gas industry, you could give Temitope the connection so he can propose his novel solution. Thank you very much.
Thank you, Chairman. Thank you very much.
Thank you. We're going to move to the second presenter, Ms. Nyanga. She's going to walk us through her own research. Thank you.
Hello, everyone. I am going to share my screen now. Okay. All right. It's nice to have the opportunity to present. I will be talking about the effect of post-annealing on the performance of zinc oxide, polyhexythiophil, a blend of polyhexythiophil and a butyric acid methyl ether used to produce an inverted geometry organic solar cell. So this study actually originated in Nigeria. It followed my master's project, and we made some hypotheses and tried to improve on it so that we can have better performance of the device. So organic solar cells are quite interesting because they are low-cost solar cells, and for the industry, they are attractive because they can be mass-produced very easily. The row-by-row production makes it very easy. They are fashionably designed in that you can use them to wrap your cars, fix them to your walls, the windows. So you can actually use them as a power source and incorporate them to your designs, which makes them quite attractive for commercialization. However, the challenge of this organic solar cells is that they have poor performance when it comes to power conversion efficiency. And to improve, many researchers have tried to use different approaches, such as the donor acceptor sensitization, incorporating blended junctions and other semi-conductors. So in this study, okay, a little about the history and the trend and the research. Starting from 2000, the organic solar cells attracted a lot of research interest following the outstanding features I had presented earlier. So in this study, we tried to fabricated the polymer blend of hexathiophil and the butyric methyl ether polymer based on an inverted organic geometry or inverted architecture. Then we annealed the active layer at different temperatures, and then we studied the effect of annealing on the performance of the device. Usually, the organic solar cells, the inverted geometry, has this structure or architecture. And the working principle is that sunlight or a light source falls on the cell, and then charges are separated, and you can actually use this as separation of charges to load your device. So this is the framework that we adopted. And the hypothesis which led to in the study is that we said we're gonna introduce this layer, hoping that when we introduce this heat reflecting agents layer, that it will enhance light absorption, which will automatically translate to improving the power conversion efficiency of the device. So our method was that we built on an ITO coated glass. We incorporated the heat reflecting material and then the polymers and a metal electrode. And this is the structure of the device that was built. The results showed that annealing the active layer actually increased UV absorption. So we can see from figure 2A that the wave length between 450 to 650, increasing the absorption layer, increased absorbance. And the power conversion efficiency calculated for these devices showed this is without the heat reflecting layer, and then this is with the zinc oxide layer. So you see from here that the power conversion efficiency was increased, and the optimum annealing temperature was achieved at 130 degrees centigrade. So we have almost 61.37% improvement in increase in efficiency of the solar cell that was fabricated. So in conclusion, post-annealing of active layer increased power conversion efficiency of the organic solar cells. Optimum annealing temperature was found to be 130 degrees Celsius compared to studies in the literature and from our previous study. The results tallied, and the optimum device fabricated had a power conversion efficiency, which is actually a bit low, but also better than others reported in the literature. An increasing annealing temperature of active layer widened the absorption spectrum of our fabricated device. Thank you. Questions, please.
All right, thank you very much for the short and insightful presentation. That was pretty much very powerful. We would like to welcome some questions, but as a reminder, if you look at the chat box, there is a link where you can send questions, recommendations, assessment, and evaluation to Uyanga. We'll be glad to have that. So in the meantime, if you have any question, please could you let us have them, please?
Hello, can I come in?
Okay, go ahead. Yeah, thank you.
Please.
Yeah, thank you for the nice presentation. It's actually a good study. But I don't know if you consider the influence of different annealing temperatures, or you only consider only one temperature for your study?
I consider them 4 different temperatures. At room temperature, when the study was conducted, and then we varied annealing between 120 and 140 degrees Celsius.
Okay.
Okay, thank you for that. Another question, please. Okay, so in the absence of another question, I would like to ask you a couple of questions. The first comment I want to make is that if you are trying to show us the efficiency chart, I think it's recommended if you can use from the National Renewable Energy Lab, right? It is more reliable. The second question I want to ask, do you get what I mean?
Yes, actually the National Renewable Energy Lab chart is quite congested, so that was why I used this. This brought out more on the. Can you hear me?
You're gonna have extraction from the chart.
Okay.
Right. And also your data is up to 2015, and we're already in 2020.
Yes, I noticed that too, but this was the one that made these my points clearer, so that's why I chose it.
Okay.
That showed the spike. Yeah.
Right. The next stuff I want to talk about is that when I was going through your abstract, it was pretty much interesting because with your method, you talked about being able to improve the morphology, the fill factor, the power conversion efficiency. But I mean, if you look at as at today, we have efficiency between for your solar cell, organic solar cell, we have between 4 to 9%. Yeah. I mean, you are still lagging behind. So I want to ask, I mean, what is the science behind the morphology improvement? Because when you talk about, when you realign the morphology, you are simply looking at, I mean, improving the, the absorption, right? The light absorptions and perhaps converting it to a power, to current or whatsoever. So what is the science behind your method being able to improve the morphology that leads to the improvement of the efficiency?
This study is actually unique in the sense that a large part of it was carried out in Nigeria before I came to Hong Kong. So that was about 2 years ago. And that was actually what attracted researchers in City University. It's something we hadn't achieved in Nigeria before then. Yeah. So, and you can imagine the situation of the labs in Nigeria. So for us to have been able to achieve this, we must have put in a lot of carefulness and to get the results. So should this work have been carried out here, where we have everything in place, I'm sure we can achieve even more than the reported 11% power conversion efficiency.
Yeah, so finally, as a comment for you, you know, I like what you are doing because from literature, we realize that the organic solar cell is definitely the future, right? So if you can stabilize it, if you can further the work, escalate the work, then I think it's going to make more sense. And one thing I also noticed in your work is that with the arrangement that you are giving to us, I mean, it looks like an heterojunction, right?
Yes.
You should definitely have very good conversion efficiency. So you have to go back and reassess your work and see how best you can improve it further. Thank you for that presentation. It was quite nice.
Well noted. Thank you very much for the opportunity.
Thank you very much, all presenters. At this point, we'd like to pass the time to the chairman to continue. Thank you.
Hello, Dr. Akini, are you there? You want to take over? Okay, sorry. We already had a private chat, so I thought it was. We move to the last section. Thank you so much for your patience. So the last section is going to talk about law and commerce. So I want to hand over to Dr. Soyinka Oluwale, who is going to coordinate this section. So it is over to you now, Dr. Soyinka.
All right, thank you, Mr. Adeoti Blessing. And then again, I want to say thank you to all participants. Thank you for your waiting, and I hope you've been enjoying all the presentation. And then I hope they are worthwhile. We've learned so much. And then we are going to the fourth section. And I tell you, this section